Hello and namaste, viewers and judges. We are Team Tattva from MIT WPU, India. Since we're presenting all the way from India, we won't start by boring you with the mundane concepts of net zero or with the bland statistics that billions of tons of CO2 is released into the atmosphere. Instead, we would like you to imagine and envision a world that is a result of no regulation, no carbon capture, and no students working on a modular system to help the society from ground up. This is what we will be a part of. A world where stepping outside requires a mask, where visibility drops to a few meters, a world where your very existence itself is a miracle. This is not fiction. This is the trajectory we are currently on. Over the past 120 years, global CO2 emissions have increased nearly 19 times, driven by the fossil fuel use. And despite global awareness, emissions are still rising. If no action is taken, emissions are projected to reach around 49 gigatons per year by 2050. This red curve represents the business as usual scenario, and this is exactly where we are heading. The problem is not just emissions, it is who is emitting them. Today, while some countries are reducing emissions, others are increasing them much faster. By 2050, nearly 80% of emissions will come from high growth economies, completely offsetting global progress. The world is not winning this fight, it is losing it. But emissions are not just numbers, they have consequences. Figure 1 shows how even a small rise from 2 to 4 degrees Celsius leads to extreme global warming. This is not just temperature change, this is a shift in where humans have to survive. Under current conditions, climate change could cause 83 million deaths by 2100. Beyond 2 degrees Celsius, impacts rise sharply. At 4 degrees Celsius, we see over 4 million deaths per year. But if action is taken, we can reduce these deaths from 83 million to just 9 million, saving over 74 million lives. This curve shows a critical insight. The impact is not linear, it accelerates. Emitting just 4,000 tons of CO2 statistically results in one human death. And these deaths are not just due to heat, they come from collapsing systems food, water, health. Climate change doesn't act alone, it breaks everything. This is no longer an environmental problem, it is a human survival problem. And yet, the future is not inevitable. Because the same carbon that is causing this crisis can also be captured directly from air. This is where DAC comes in, or direct air capture. DAC allows us to remove CO2 already present in the atmosphere, not just prevent emissions, but reverse them. Unlike traditional methods, it works independent of emission sources, making it a universal solution. And this is exactly what we aim to do with a modular carbon capture cube. The system designed to work at a ground level, scalable, deployable, and accessible. Because solving climate change is not just about reducing emissions, it is about removing what's already there. So, this is why we are here, racking our brains from across the seas to come up with a solution for the persistent problem of carbon capture.
Okay, so now that we've talked about the current emission situations as well as the need for direct air capture, let's quickly talk about the market analysis. I don't lie when I say this. Carbon credits represent one of the fastest growing global markets today. The market has already crossed around $800 billion and is projected to exceed $6 trillion in the upcoming decade. This rapid growth is being driven by global climate targets, increasing carbon regulations, and corporate commitments towards a net zero emission. What this tells us is very simple that carbon removal is not just an environmental need but a massive economic opportunity. Firstly, we talk about more on the demand drivers. The demand for carbon credits is being driven by three key main factors. Firstly, is your regulatory pressure. Governments are often introducing carbon taxes and compliance system that requires industries to offset emissions. Second factor, which is the most important one, is your ESG expectations. As you can see from the graphs, investors now evaluate companies based on their sustainability performances. The third factor being corporate net zero commitments. Companies like Microsoft and Amazon are actively purchasing carbon removal credits. Together, these forces make carbon credits not optional but essential. However, there is a critical imbalance in the market. While low quality avoidance credits are widely available, high quality carbon removal credits are extremely limited. Technologies like direct air capture produce durable and verifiable removal, but current supply is far below demand. This creates a significant gap for us and a strong opportunity for scalable carbon removal technologies. Now, building on the supply gap we just discussed, our solution not only captures CO2 but it also creates direct economic value. At the top, as you can see, we show the primary value stream, which is getting carbon credits. CO2 is captured, is measured, is verified, and is converted into high value removal credits, which can be then sold to corporations with net zero mandates. Due to high integrity of direct air capture based removals, these credits command premium pricing in the market. Beyond credits, our system also enables participation in a broader carbon economy. Captured CO2 can be further utilized to produce fuels, chemicals, or advanced materials, unlocking additional revenue streams. This dual value approach allows us to transform CO2 from a liability into a scalable economic asset, while targeting high emission industries and corporations actively seeking verifiable carbon removal. So, now we'll talk a bit more on the Indian scenario because we strongly believe that India has a very high value for renewables. So, we'll quickly talk about the Indian scenario at hand.
So, our team is tackling the ultimate frontier for climate tech, direct air capture. In the Indian context, direct air capture is no longer a future technology. It is a strategic necessity. The Union Budget 2026-27 has unlocked 20,000 crore rupees for carbon capture, utilization, and storage. And our DAC approach specifically targets the indigenization of solvents. By utilizing rice husk biochar, an abundant Indian agricultural byproduct, we reduce capex by up to 40%. Through the VGF framework, making direct air capture commercially viable and for the domestic market. The economic engine of our project is the Indian carbon market, set to be fully operational by October 2026. Unlike traditional point source capture, direct air capture credits are high value removal credits. Global markets, these command a premium. By generating carbon credit certificates through atmospheric removal, we provide a high ROI pathway for underachiever sectors like aviation or shipping that cannot easily capture at the source. With market estimates between 600 to 900 rupees per ton, we are trying to provide a high ROI pathway, creating a policy driven growth market for our queue.
So, hello again. I'll quickly discuss about our mechanism and the sorbent that we've proposed. But before going forward, we would like to highlight that our team strongly believes that the sorbent that we use or the technologies that we'll put forth should always focus on being carbon negative along with being efficient. So here's the sorbent that we have proposed. The sorbent consists of solid supported amine adsorption mechanism which uses hierarchical composite sorbent. The sorbent consists of SBA15 mesoporous silica which is functionalized by PEI, supported on activated rice husk biochar. This creates a nice hierarchical structure where each component plays a specific role, which we'll further discuss in enhancing CO2 capture. So, the biochar acts as a macroporous skeleton for providing low resistant pathways for bulk gas transport. So, we think that kinetics are the main thing when we are dealing with direct air capture because our concentrations reduce to as low as 420 ppms. Hence, providing low resistant pathways towards your actual sorbent that does the ChemE sorption is must for direct air capture mechanisms. So basically these large pores allow atmospheric air to rapidly diffuse into the particle. Within this structure, SBA15 provides ordered mesopores which offer high surface area and serves as active sites for PEI loading. So this hierarchical design that we have proposed, it overcomes mass transfer limitations. Unlike pure silica systems where pore blocking can occur, the biochar scaffold enables the efficient delivery of CO2 deep into the sorbent, improving overall utilization of active sites. So at the molecular level, CO2 reacts with the amine group in PEI to form a reversible carbamide species. This chemisorption mechanism allows selective and efficient CO2 capture even at very low atmospheric conditions. So the core concept that we have is what we've made a hierarchical composite where I have SBA15 which is mesoporous which is loaded with PEI which is our molecular basket, and all of this is nicely resting on alkaline activated rice husk biochar. So let's go further and discuss our proposed sorbent production mechanism. We follow a very standard procedure for PEI loading onto our mesoporous silica which is SBA15, and this is the overall process flow for the sorbent production mechanism. I would like to highlight that we have added an optional heat treatment to increase our structural stability for our composite, and the mixing of biochar will be done through either ball milling or just physical mixing. Now, this sorbent production method is very low in terms of energy requirement. It is very scalable and very industry relevant, and also it utilizes waste biomass, which in turn adds to our carbon negativity. So the question at hand is, why did we use solid supported amines over liquid systems? So solid supported amines were selected over liquid systems due to their significantly lower regeneration temperature, operating at 60 to 80 C compared to nearly 900 C for hydroxide based systems. This 60 to 80 C band is based on a regeneration method of temperature vacuum swing. This makes them far more energy efficient and practical for our setup. And among mesoporous supports, SBA 15 offers the best balance of cost and performance, providing high surface area and ordered porosity at a lower cost compared to alternatives such as KIT6 and KCC1. Okay, so let's talk about the selection criteria for selecting our amines for our system. So we went ahead and we selected branched polyethylene amine due to its superior thermal stability and resistance to volatilization. Compared to smaller amines, branched polyethylene amine shows significant lower leaching during regeneration, which improves solvent longevity and safety. This makes it highly suitable for cyclic direct air operation. As shown here, branched polyethylene amine maintains high adsorption efficiency at medium loading while exhibiting minimal degradation over multiple cycles. This balance between performance and stability is critical for ensuring consistent operation in repeated absorption and desorption cycles. We further selected PEI 600 due to its high nitrogen content, which enhances CO2 adsorption capacity. This allows for more active amine sites per unit mass, resulting in higher capture efficiency under DAC conditions. We compared PEI with other amines as well, such as TEPA and TEA. While TEPA suffers from volatility and leaching, and DE presents toxicity and nitrosamine risks, PEI offers low volatility, high stability, and safer operations due to its polymeric nature. This makes it more suitable choice for a solid phase DAC system. Okay, now let's go ahead and discuss the selection criteria for our support, which is SBA 15. So as discussed earlier, our team strongly believes that higher kinetics are must for direct air capture operations. So we went ahead and we started looking at kinetic models for various mesoporous materials. The above shown kinetic model shows that PEI supported on SBA 15 achieves higher adsorption capacity compared to other supports. This indicates faster reaction rate and better utilization of active site, which is essential for shorter duration TAC operation. As seen in the data, SBA 15 maintains strong adsorption performance even after PEI loading. Its mesoporous structure preserves accessibility while providing high surface area, enabling efficient CO2 capture without severe pore blockage. So this is the model fitting curve that we found, and we can see that SPA 15 provides the best CO2 adsorption capacity, and it demonstrates the adsorption behavior over time, showing rapid intake, initial intake followed by gradual saturation. This highlights that our system is primarily mass driven, which aligns with our design focus on faster kinetics.
Now I'll be talking about why we choose to involve biochar as a critical part of our system. This is because biochar provides inherent macropores which act as low resistance diffusion pathways, allowing ambient air to penetrate deep into the solvent structure. Additionally, biochar acts as a rigid scaffold, preventing pressure drop issues that are common with fine silica powders. And finally, since it is derived from agricultural waste, it is significantly used to reduce the cost while still maintaining the performance. This slide shows the general role of different pore sizes in the adsorption systems. Firstly, we have micropores, which are typically associated with physics absorption due to their high surface area. Secondly, we have mesopores, which allow loading of active materials like PEI within silica, while still maintaining accessibility for CO2. And lastly, we have macropores, which enable bulk diffusion, allowing air to flow easily through the structure. For our method of regeneration, we opted for temperature vacuum swing absorption because the application of vacuum along with mild heating reduces not only total pressure but also reduces the partial pressure of the CO2. This creates stronger driving force for desorption. Because of this, we can regenerate the sorbent at much lower temperature of around 60 to 80 degrees Celsius. This is significantly safer and consumes much lesser energy compared to other conventional methods. The following graph compares vacuum pressure swing adsorption with temperature vacuum swing adsorption. We can see that across multiple cycles, the adsorption capacity remains stable for TVSA, which means that the sorbent in TVSA does not degrade as quickly as compared to that of vacuum pressure swing adsorption, therefore making TVSA a far superior choice over VPSA. This slide compares TVSA with conventionally and more widely used regen method known as temperature swing adsorption. The key takeaway of the comparison is that unlike TSA, which operates at higher temperature above 100 degrees Celsius, TVSA allows regeneration at lower temperatures of about 60 to 80 degrees Celsius. This does not only reduce the energy consumptions but also reduces the thermal stress on the amine, therefore reducing the degradation of sorbent over multiple cycles. It also produces a higher purity of CO2 compared to that of TSA, therefore making TVSA an optimal choice of regen method. This slide also shows the performance of TVSA over multiple cycles. From the adsorption curves present on the right side of the slide, we can see that the adsorption capacity remains stable in the case of TVSA, therefore indicating low degradation of the solvent. And from the desorption profiles present on the left side of the slide, we can observe that applying vacuum increases the regeneration kinetics. So it can be stated that TVSA improves both regeneration kinetics and long-term stability. Now I'll be talking a bit about the degradation in amine systems. There are two main pathways. One is the oxidative degradation and other one is urea formation. Our proposed CBSA system helps mitigate both of these problems. The vacuum reduces the presence of oxygen, therefore limiting the oxidative degradation, whereas the lower operating temperatures, which are around 60 to 80 degrees Celsius, will suppress the formation of urea. So now there is some more data on how TVSA works. So the three given graphs show the performance of TVSA under varying parameters. Across the cycles, the adsorption capacity remains fairly stable, while the desorption profiles show consistent regeneration behavior. From the table present at the bottom right, we can see how operating conditions like pressure and temperature affect working capacity, productivity, and energy requirement. So to sum up, we can say that TVSA can be optimized to achieve a strong balance between performance and energy efficiency.
Our hardware is a two-in-bed configuration engineered for process safety and sorbent integrity. Because we use solid composites, protecting the bed from ambient contaminants is critical. We integrated dual-stage dust filters at the inlet and outlet. These prevent atmospheric particulate matters from clogging the micropores of our biochar scaffold and crucially ensure no silica or sorbent dust escapes the system into exhaust. This closed loop containment prevents both sorbent degradation and environmental contamination, maintaining a steady safe flow through our queue. In a DAC system, sensors are our primary safety barriers. Pressure transmitters. These are vital for detecting bed plugging. Any sudden increase in pressure drop alerts. It alerts us to filter blockages or sorbent settling, allowing for an immediate safety shutdown to protect the flow. Relative humidity sensors help us with high humidity, which can cause PEI leaching or silica pore filling. We monitor this moisture to ensure that sorbent remains in a safe operational window. Temperature indicators detects any hotspots from the exothermic heat of adsorption. Monitoring the change in temperature ensures the safe system stays within the thermal limits. This sensor-driven safety protocol ensures our cube is as reliable as it is efficient.
So I will be explaining the electronic schematic of our project. We have added electronics for the autonomous operation of our cube. We have opted for an STM32F4 series microcontroller due to its versatility and powerful performance. We have also opted for an SD card module for data logging. We have added an ENS210 sensor for measuring the relative humidity. We have added three DS18B20 sensors for measuring temperature. We have added two BME280 sensors for measuring the pressure. And we have added an STCC4DR3 sensor for measuring the carbon dioxide. We have also added an USB-C connector through which we can program the microcontroller. We have added two terminals, screw terminals, and these will be for the pump and the heater control. And the pump and the heater will be controlled by an IRL Z44N MOSFET, which is a logic level MOSFET. And this will help us switch the terminal output between on and off depending on what the feedback the sensor gives us.
Let's go ahead and discuss our novelty and strategic impact that we wanted to showcase through our design. Our key novelty lies in replacing expensive synthetic silica with a biochar based scaffold derived from agriculture waste. This significantly reduces material costs while balancing or enabling a carbon negative supply chain. At the same time, the hierarchical structure overcomes pressure drop limitations, improving overall system efficiency compared to conventional DAC systems. Now let's go ahead and talk about the safety considerations that we had during the design phase of our cube.
Speak for everyone when I say that this system is super cool. With any system that deals with chemicals and heat, we need to stay sharp. Our main concern are the fine dust particles or vapors. For this, the system is sealed shut using filters and enclosed system. The pressure and temperature regulation is of an equally great importance as the PEI starts degrading above 80 degrees Celsius. We deal with this by incorporating sensors and insulation. We use low temperature vacuum process to stop oxidation of PEI. In any system, mechanical stability is as important as its chemical stability. The air might take a shortcut, causing the system to fail. Moreover, the condensation might fill up the pores and clog the filters. These problems do sound fatal, but the solution is equally neat and simple. Uniform packing and continuous monitoring will not only solve these problems but also identify future problems at a very early stage. We are dealing with chemicals like K2CO3 and PEI, and they are not to be messed with. A PPE kit is a perfect tool to work with these chemicals. Moreover, the biochar needs to be at a critical pH of 7. The materials need to be dried completely to get the desired results. Vacuums, transistors, and other electrical equipments are prone to stress, leaks, and shocks. Like every other electronic component, we use safe connections, insulation, and gentle handling. This will ensure a long life of the system and a safe operation. Our product is nearly perfect if it weren't for science. And by that, I mean the degradation of components due to age. Someone did say that all good things must come to an end, and I would like to disagree with it. By periodic monitoring and replacement of chemicals, our system will work for an extended period of time. So you have time to do greater things for yourself and the planet. In the end, safety boils down to insulation, monitoring, and proper disposal. Keep it sealed, keep it cool, stay safe.
Technology is ready or no technology is validated without any cost analysis done. So here's our capture per year, metric tons of capture per year, and our very preliminary calculated capex and opex that we found. So all in all, our cube would cost around 700 for capital and about $85 per annum for its operational expenditure. And yeah, thank you so much guys for going through our entire virtual qualifying presentation video. Thank you so much. This was Team Tattva from MIT WPU AICHE student chapter, and we eagerly await any and all questions that you guys would have. And yeah, thank you so much for watching.